In this next example, we're asked to compute the angle between body diagonals of a cube. And in this case, the cube has a length on each side of 1. So in the xy plane, this point, for example, would be an x value of 1, a y value of 1, but then a z value of 0. Over here, for example, there's no x value or y value, but there's a z value of 1. And so the vector x, we'll call it x1, that takes you from the origin across the body of the cube to point P1 has components 1, 1, 1. But we need another body diagonal. We would like it to proceed from the origin to another point on the cube. But as you notice, let's say take this vector as an example. That is not actually a body diagonal, that's a face diagonal. It goes across the face of the cube. So we can't use that choice. And it turns out we can't use any choice proceeding from our chosen origin, but we do need another vector because the strategy is to take the dot product of two appropriately defined vectors and then use the definition of the dot product to solve for the angle. Now, the lesson here is that vectors don't have an origin. They don't lose their definition, in other words, their direction and their magnitude, if we change what the origin is. And so going from P2 across the body of the cube would require this origin, so we can call that maybe O2. And so to illustrate what that body diagonal would look like, we could draw that vector and give it a little arrow at the tip. So the question is, what is, and we'll call that x2, and the question is, what is the angle between x1 and x2? We need to call this vector x2. But what are even the components of x2? Well, what is the value of this point here? So it has an x value of 0, but it has a y value of 1 and a z value of 1. Now, we know that the change in x in going across the body diagonal would have to be 1 as well, and if you wind up at 0, the only appropriate vector would be negative 1, 1, and then 1. Why is that? If you think about this, if you look at x2, in which direction is it proceeding along the x-axis? It's actually proceeding along the negative x-axis. It's going this way, right? That this is the positive x-axis. That's the negative x-axis going into the page, if you will. And so if it's going in the negative x direction and its change in position is just 1 unit, then it has to be negative 1 for the x component for x2. If you take the dot product, then that's going to be the magnitude x1 times x2 times the cosine of the angle between them. Now we don't know the angle. We could easily compute the magnitudes, and the dot product is quite simple. So we're going to do the dot product in shorthand. So I'm just going to draw a line under the x1 and x2 definitions. Now if I take 1 times negative 1, that's just a negative 1, plus 1 times 1 is 1, plus 1 times 1 is 1. So two of the terms cancel, and you're left with 1. So the value of the scalar value of the dot product is 1. Now we need the magnitudes of these vectors. Again, in shorthand, it's going to be the x component squared plus the y component squared plus the z component squared for x1. We're going to take the square root. Turns out that's the square root of 3. And then this should be the same magnitude. It doesn't matter that for x2, it shouldn't matter that one of the components is negative. Negative 1 squared will just be 1 anyway. 1 squared. But on a deeper level, the uh, the cube isn't changing dimensions in any direction. So the fact that we needed a different origin and one of the vectors was negative, it shouldn't change the magnitude. So we get the same magnitude. And so we have a pair of square root of 3's cosine theta. Root 3 times root 3 is just 3, and if we divide both sides by 3, then we get 1/3 is equal to the cosine of theta. And so our angle is just merely the arc cosine of 1/3. And it's a good sign that the angle reduces to a simple algebraic expression. We didn't get some complicated expression for the involving a bunch of terms that seem to appear out of nowhere. It's just a simple fraction, a arc cosine of a fraction. So the lesson here is that comparing the dot product to the one definition of the dot product, comparing the component by component scalar result for the dot product to the definition of the dot product is useful for obtaining one of these components, or the magnitude of one vector or the other, or the angle. So that's a useful technique. And then also remember that vectors don't have an origin. Vectors can be shifted around, translated. It does not change a single thing about their properties. The two fundamental properties are the direction and the magnitude. So under any sort of transformation, rotations, inversions, things like this, the direction and magnitude should be retained.